12:30 sharp. We're supposed to start. Obviously, you realize the lectures are videotaped. That's why I have to start exactly at 12:30. I suppose I have your permission to videotape you. You're not actually on the video, but if you say anything, also you don't have to worry because it's not going to pick you up. The only microphone is with me. But the lectures are going to be videotaped and posted on the website of the course and also on, what's the system? What's not the name? I forgot. Sakai? Something like that, okay? All right. But, we put the lectures on YouTube, so you can download them directly from the lecture notes. The course website, it's under construction, which means it's only, the link is there. The rest is going to be up when I manage to get some sleep after some 12 hours jet lag, okay? So maybe tomorrow or something, certainly before the next lecture, I hope to have this thing up with today's lecture and video as well. Let's see. The class is Tuesdays and Thursdays, 12:30 to 1:45. I know there has been lots of changes on the timing. It's really not something I control. When you use a lecture room like 126 de Bartolo that has videotaping, everybody wants this room. So it's very difficult to... We're all set. Yes, everything is on. Yeah, thank you. Thanks for stopping by. This room is on high demand. So we were in, then we were out, in and out. So we are in as of today. There will be 2 lectures, Tuesdays and Thursdays. And maybe not every Friday, but once in a while, we're going to have recitations to get you help with the homework. And in addition, when there are missing lectures, I'm going to use Fridays to cover up for that. So let's see what else. That's my email address. Whatever information you need, I'm going to try to provide it on the course website. Okay. There's a lot up there, regarding the course objectives. This is not an application course, right? I don't usually teach application courses. So this is a course on the fundamentals of probabilistic graphical models. And I remember someone had asked me in the past, what's probabilistic graphical models, thinking must be something graphical. Probabilistic graphical models is a concept. It's a way to work with many random variables. And if you think these many random variables are somehow interconnected because they are correlated, there is a graph. And then maybe we can use some graph theoretic approaches to do inference fast. But don't expect to have a problem where there is a graph and then you say, oh, do something with this graph. The graph is there. All right, so you have to think of something being represented as a graph, and I think in some sense that's the most difficult part of the course. Being able to actually visualize on what is a good model to represent relations between many random variables. Okay? So I'm going to try to give you all the fundamentals to do inference in graphs, and when I talk about inference, I refer to Bayesian inference. I'm going to discuss both directed and undirected graphs. Maybe people in social sciences, psychology, they like directed graphs. People in science and engineering, they like undirected graphs, but we will see that somehow we can connect the different types of graphs. If we learn one, maybe we can learn the other types quite easily. Obviously, I'm going to give you examples here and there that represent the potential of using graphical models, from standard machine learning problems to computer vision to doing scientific computing to some applications of natural language processing, computational biology. I don't believe we have anybody from biology in the audience, do we? Okay. Obviously, nobody does anything related to this type of thing, so we don't have any contributions from students this year. All right. So the course is appropriate basically for students in math, statistics, and computer science, for students in engineering that have good mathematical skills, that's very relevant, and students in all areas of sciences, including cognitive sciences, biology, physical, chemical, etc. Some of these courses in other universities are so popular. I noticed, for example, if you go to Stanford, the course has more than 300 students attending, okay, because there's interest from every direction, okay. Here you are the selected ones at Notre Dame who have the courage to come and attend this lecture today, and I hope to see you on, what's the next lecture, on Thursday as well, okay. And I hope to see you the day after I give the first homework, because usually that's when the class population goes down by 50%, okay. Now, this is not a course just to get 4 credits. I am assuming the only reason you're here is because you want to learn the topic and integrate it with your research. And I'm going to help you in doing that. But if you just need 4 credits, this is not the right course for you. Okay? I want to, this is a very hot, important area in many ways, and I'm going to educate you, but to be able to learn it, you need to have an interest on the topic. If you don't, this is not the place to be. Now, the course, is going to be one of the core courses on the new Center for Informatics and Computational Science. It's basically the second in sequence from a course that I taught on Bayesian statistics in the fall. You don't really need the previous course, and if you need something, well, I mean, when I say you don't need it, you need everything, right? The more you know, the better. But I cannot expect you that you know what was covered in the previous course. So when there are some fundamental concepts that we need to bring in, I will either cover them in this course, or I will give you notes basically to read about them, okay? And it is possible that I'm going to go back to some of the topics covered in the fall anyways, but try to address them in a graph theoretic manner. Okay, so new algorithms to problems we covered, for example, related to data simulation in the fall semester. So, you need to know probability theory. If you don't know anything about probability theory, I will disappoint you. You need to know the fundamentals, at least, Bayes' rule and the likes about Bayesian inference. And if you have taken even an introductory course to machine learning, may be useful, okay? Machine learning for me means computational statistics. So whatever we need, I will bring it back for your convenience, but it is going to be helpful if you have a book in your desk that you can look for information, okay? And I'm going to give you lots of readings that you can go through this semester and also after the course is over. You need to know programming, because we will make an effort every homework to have a computational problem. And we're going to try to do this even on the first homework. Usually the first homework is to do hand calculations, but we're going sort of to try to give you a computer assignment simply because we want to emphasize this is a course that uses computers. It's not to do hand calculations. There's too much computation, and hand calculations will not help you to do any serious problems. Okay? All right. Like in the fall semester, I'm relying on help from others to run the course. So Dr. Suvik Chakraborty, that is next over there with his Mac, is volunteering to help with some of the recitations, preparing some of the homeworks and the solutions, and also doing some of the grading. And so he's going to run the recitations and maybe once in a while give a lecture or two when I'm out of town. So the homework is going to be submitted electronically to this email address. I'm going to provide more information on the website in the format that you need to submit the homework. This address may change actually by tomorrow. That's why I said this email address. This is a Google email account, but we may design one just for this class. Okay. I noticed some of you look, oh no. Yes, we like typed homework because if you submit, especially computational assignments, and you start writing by hand, there's no way we can figure out what you're writing there. If you type something nicely, it is very easy to know what is going on. Okay. So indeed, we prefer typed homework, but some of you are lazy, and I'm referring to my students, my own students. So for those who are lazy, you can scan your homework and submit it as a PDF attachment. Okay? If you do these things by hand, trust me, you will identify 90% of the mistakes in your homework. Just by typing it slowly and looking at it, saying, oh, it doesn't look good. And if it doesn't look good, it means it's wrong. Okay? But if you type by hand, it never looks good. So you never have to ask, is it right? Because most of the time it's wrong. Okay? So we like typed homework. Not to mention, you know what, if you type this nicely, tomorrow you go for a job interview and you say, yeah, I took this course and here is what I did. And that counts a lot. Okay? Because this is not intro to happy hour type of course. Let's see. There will be information on how you have to attach your homeworks and how to name your submission. Okay, so I will give that information on the website. Books. I'm going to start actually in different orders from what is given here. This book by Michael Jordan, An Introduction to Probabilistic Graphical Models, is actually what is used in most universities for reading, and it's actually sort of, everybody says in preparation, preprint. This book has been in preparation for 25 years, which means Professor Jordan has given up basically because things are changing so rapidly. It's like, what's the point of finishing this book now? Okay, and so this is actually the easiest and the most insightful reading that you can have. And for those who register in the course, I am going to send you PDFs of, I shouldn't be saying this on tape. Somehow you will go in the library and find it. Okay? All right. Let's see. If you really want to, if you do research in this area, a heavy book that you need to have in your desk is the textbook by Kohler and Friedman. It's more than 1,000 pages, maybe 1,200 pages. Has a lot of information. Some we will cover it in this course in detail. Some other details we don't need them. But certainly this is the state of the art, both in theory and algorithms. So this is, a recommended book basically for, to have. The textbook that we used a little bit last fall by Kevin Murphy has, it's like an encyclopedia of machine learning. It's not really a readable textbook, but it has a lot of new algorithms, a much more modern approach, and it has a software also that goes with all the examples in the book. So it's highly recommended, right? And it is actually less probabilistic than, for example, Jordan's preprint. Okay, it likes to use point estimates for fast inference for most of the algorithms, but there are, I don't know, 6-7 chapters I think on probabilistic graphical models, and we will cover at least the essential parts of those. Bishop has one chapter on probabilistic graphical models that is actually an ideal read. If you want to know everything about this course, before we even start, to get a good sense, let's say this week, you should read, what chapter is it? 8? 8. So if you read chapter 8, even just without the details, all right, just going through it, it will serve you extremely well because it has everything, no proofs or anything like that, but it has a lot of insights as to what probabilistic graphical models are and how to go about it, okay? So certainly this could be a good start point, and also if he has has many other things that utilize the machinery of probabilistic graphical models that we will also use in this course. It's extremely readable. It's most probably the most readable book on machine learning in the market, and even though it's about 20 years old, you will find it, at least when I read it every other day, I find something new there, okay? So I recommend all of these books. Okay, grading, so we're going to have 6 homeworks. The homeworks will be 60% of the grade, and it'll be a project 40%. For some, maybe that's too much, you know, but if you think about it, no exams, no midterm, no final, nothing, okay? So this is a gradual course. We don't operate the classical way, but the expectations are higher than having an exam where you write something on one page and say, congratulations, you passed the course, all right? The project, the format may have to change a little bit from those who took the course in the fall, because I was very disappointed with the attitude of many students here when it comes to the course, to the project. I gave freedom to everybody to define their own project relevant to the course, and I can tell you there were at least 7 students who came up with a new definition of their project about 3 days before the presentations. I mean, that's not normal. That's ridiculous, okay? So, so I don't know exactly how we're going to do it, but I'm going to think in the next 2 or 3 weeks, but the possibility would be to actually literally throw you 10, 20 projects and say this is it, and here are the references, pick up whatever you like and do one of those, and you cannot change it. All right? Or we may do it as last fall, but with strict guidelines that you change project means you get 0 grade in your project. We cannot allow basically a week before the presentations to redefine what the project is. And I'm not talking modifying a little bit, I'm talking about going from A to Z, okay? Not to mention going from A to Z and Z having no relation to the course at all. Right, so that's not good, okay? So certainly I want with the project to give you an opportunity to do something that is relevant to your research, right? So that not only you benefit because you learn the material of the course, but also you benefit because the course impacts your own research, and that's very important, okay? So now, because of so the project is going to require a report, which is going to be limited to 6 pages, a written presentation like PowerPoint or Beamer, and an oral presentation. And because we had headaches in the fall with scheduling these oral presentations and videotaping them, have not seen any of the videos yet, by the way, of these presentations yet, because they have not been provided to me. But what we're going to do to avoid all the headaches we had, we're going to take maybe the last 3 or 4 lectures of the course, and we're going to have the presentations in class. So you're going to be on this real video, and there will not be any issue because the videos are automatic. Okay? So we don't have to worry about, sorry, there is nothing available in May. Sorry, in June this building is closed. In July is open for something else, and etc. We're going to do it in class, even if that takes lectures. So be prepared that the project will be due way before the end of the semester. Way means, you know, 3 lectures at least before the end of the semester. So we're going to have to move on the projects quite soon. Okay. The syllabus is very sort of preliminary. So some of these topics we may cover them in lots of details, but some not. We're going to discuss, as I mentioned, directed and undirected graphs. This can be of interest to everybody, but mainly, in social sciences, natural language modeling, things like that. Markov models are basically essential for people who work in scientific applications. We're going to do lots of algorithms for data simulation problems, starting with basically reformulating everything that you may already know from other courses or not. Some of these topics, we cover them in the fall. So ideas, for example, of doing dynamical systems with particle methods. Now we will see how to develop the same identical algorithms, but with a graph theoretic approach. So for example, you can think of doing Kalman filtering and generalizations almost with no effort using algorithms on graphs. Nothing new, but at least the setting. With graphs, you will be able actually to develop your own algorithm if you want to, that is extension of standard methodologies that have been around for 20, 30 years. We're going to spend maybe more than a few lectures, maybe anything from 5 to 10 lectures to discuss inference in graphs. And this concept of exact inference, of course, is it's not always possible. So we are going to start with this, and then we will cover as part of the exact inference ideas of belief propagation, the Jackson tree algorithm, variable elimination, and the likes. We're going to discuss about approximate inference using generalizations of mean field type of algorithms. So this is an important area. And it's actually an area that literally goes hand to hand with graph theoretic algorithms. So this will be an essential part of the course. And if we have time, I think maybe we'll spend 2 to 3 lectures to discuss on how do we learn the structure of a graph. So if somebody throws you realizations of a few random variables and you want to figure out how they're correlated, how do you do this? How do you come up with learning the structure of a graph? And of course, we realize that this is a very difficult open problem. All right, so this is actually a fantastic area to do a PhD. Not one PhD, you can work for 100 PhDs, because I don't believe this problem can be scaled, for many random variables. All right, but it's an important topic that needs to be discussed. So the lectures will be videotaped. I think within an hour or two of the lectures are available on Sakai. When the website is up, if not today, tomorrow, we will post these videotapes on YouTube, so there will be the YouTube links there. The lecture PDFs will be posted. I hesitate, actually, I have to think about this, if I want to post the lectures like we did in the fall, so that you have them in front of you during the lectures, because I was observing certain individuals in this room that they're still here, okay, during my lectures, basically doing nothing else but just looking at the computer. That's not the way to go. I mean, why are you, if you're going to look in your computer, you can look at home, right? Since the videos will be available, there's no need to come here. I mean, you make me feel good, of course, if you come, and I appreciate. But I think the idea is to being able to benefit even partially by listening in person to these lectures. Okay, but for sure the lectures will be posted, if not before, immediately after, in the afternoon of the same day. There will be lots of references of papers and books and things like that that I will link to the lectures. So consider those as very useful readings. And also there will be a lot of software links that you can use as well. All right, what I forgot is, because we're videotaped, I want to encourage questions, but I'm going to have to repeat your questions because otherwise nobody will listen to anything. Okay? So let me stop there. Any questions about the structure of the course? Really, there's no structure. I mean, we do anything we want to. We can change our mind tomorrow, all right? We're interested only to learn and not to go from A to B to C because there's no such a thing, okay? So, and feel free to take advantage of that. Any questions? Of course, the question I have to ask is, how many of you will stick with us on Thursday, all right? And I hope everybody, all right? Bring your cousins too, okay? We need all the support we can get. I mean, one of my students is teaching now at Purdue a similar course as the one we taught here in the fall, more or less similar, a little bit more basic, but he told me he had more than 60. They had to limit the class attendance to 60 because there were students from everywhere interested, but you know, here we're a small population, so we don't have the luxury of 60. 20 is actually a great number for a graduate course, okay? But you guys need to not to give up when I give homeworks, okay? If you do give up, I'm sorry for you. All right. So no questions? Any questions? Just to entertain me. No? By the way, we have, I know we have at least 10 students that will be listening to these talks from various places overseas, okay? I have been surprised that receiving mails of students from certain universities in China that they even do the homework and they submit me corrections to the homework, okay? So, and corrections to the software of the homework, okay? So, and I have seen the impact some of these lectures have had on their research, so it's quite rewarding. Okay, so we're going to start with sort of some elementary introduction to probabilistic graphical models, discussing some terminology and maybe one or two basic examples. I am not going to do any mathematics, any equations or anything like that, but so if you see saying things that really require a lot of explanations, keep in mind I'm going to come back to those topics and discuss them in detail as we go along, right? So this is just to give you a flavor of what a probabilistic graphical model is and what the type of problems we're interested in. By the way, in addition to the video lectures, from our course, if you search with the concept of, you say, probabilistic graphical models, you will find notes from many short courses, and here I have, Zubin Garamani and Chris Bishop have a series of lectures on probabilistic graphical models with videos and PDFs. But you can find online the Stanford courses and many other universities, the courses from Cornell, etc. So you can sort of, if you have questions with a certain topic, if you search, you'll be able to find a lot of resources. Okay. The good thing is this area of machine learning is an area of a very open society that likes things out there to the open. Okay, we don't hide anything. Everybody can actually benefit, and we like it that way. All right. So where really probabilistic graphical models is to model the relations between many random variables. Okay. So now effectively will be a way to produce the joint probability of these variables. So x here is a vector. So the probabilistic graphical models will give us sort of an efficient way to model this distribution pi of x. And something that we will need to be able to take advantage when we work with graphs is we're going to be able to account for the independent relations between these variables by somehow dropping some links on the graph, as we will see shortly. All right, so if I have these two variables and they're not connected, that has some implication, probabilistically speaking. So the idea here would be that the joint probability distribution, when it is factorized according to a graph, or a graph is factorized to model the independence relations inside this probability distribution, if we do that, we will be able to take advantage of inference algorithms that scale very nicely in graphs, all right? And some of these algorithms use completely graph theoretic sort of arguments, and so they're very convenient. Now, if I give you, let's say, 50 variables and you learn the joint probability distribution and somehow you can factorize it in some nice way, the main interest will be to do inference, which means if I know, let's say, these 10 variables, what's the probability of the remaining variables, all right? So we're going to have to do somehow, develop some algorithms that will allow us to compute marginals and conditional distributions out of this joint distribution. The idea is if you know the joint, you should be able to do lots of things cheaply, and in particular that will be the case for graphs. Now, when you have a joint distribution like that, you will always have a lot of unknown parameters to define the joint distribution. So one of the tasks in a probabilistic graphical model is to figure out what those parameters are given realizations of some random variables. Okay? So we will see examples of that. So, probabilistic graphical models is basically probability theory plus graph theory. Okay? We want graphs because with graphs we can visualize the independence relations between the many random variables. And once we do that, we can motivate lots of new algorithms. I mean, in the past, I can tell you when I was interested in solving some weird multi-scale problems, I was always visualizing how this may look like, and everybody thought I was an idiot because somehow they couldn't see how probabilistic graphical models can be relevant. But if it is here, then you should be able to put it in a computer program. Okay? So visualizing the structure of a probability model, I think, is essential to get nice algorithms. All right, so we're going to develop algorithms that take advantage of this graph structure. So we're going to be able to do inference, learning, and all of these things effectively in the graphs. And the ideas, for example, of these message passing algorithms will be something that you cannot do without a graph theoretic approach. So the benefits, you gain insights into the model, you look actually graphically, and you can say lots of the things as to how the random variables correlate to each other. You can develop many new algorithms by playing with the structure of the graph. And most of the inference we will do in this course can scale nicely simply because of these independence relations that are implied by the graph structure. And actually, I can tell you, that's why I told you don't need to know anything as a background. All the calculations always in machine learning, they're nothing else but applications of the sum and product rules of probability. And we will see this starting on Thursday when we develop simple things and graphs. So really, if you know the definitions of what probability is and what the sum and product rules are, then you're ready basically to do lots of nice things with graphs. All right. I told you that don't be scared. I throw lots of concepts because we will develop all of this in separate lectures. So I'm just throwing this as an introduction. So the graph is going to encode whatever independence assumptions exist for my many random variables. All right? And basically, we will be able to factorize the probability distribution on a graph, or given a graph, we will know what type of factorization the graph implies for the probability distributions that we define. The idea is that somehow this factorization of the joint probability distribution on the graph will be with local functions that are defined on the nodes of the graph. So these local functions will be different things for directed graphs, which we also call them Bayesian networks, and will be different for undirected graphs that also we call them Markov networks. Okay, but the idea is somehow a joint distribution between many variables can be written as a product of local functions. And this is great, right? But it's also physically motivated because if, for example, you think spatially many random variables, the variables here don't depend on the variables there, right? Correlations are of local extent. So somehow, if you can arrange these things in a graph to have a similar nature, you will be able to do lots of work that is local. And from these local functions, you will be able to basically build this joint distribution of the many random variables. By the way, when I said some variables are here and there, this is in the spatial context or in the time context, but the graph can be a very abstract entity. It may have nothing to do with space or time. Okay, so don't, again, depending on the type of things you're interested, you can envision different scenarios. So Bayesian networks are probabilistic graphical models that are defined on directed graphs, and I'm going to show you an example shortly. And these Markov random fields, these Markov networks are basically probabilistic graphical models for undirected graphs. So these are the main two types, all right? And you can have some graphs that have some directed components, some undirected components, and also you can pose this in sort of some unified way using what's called factor graphs, and we will discuss those as well. So actually, after a few lectures, there's no point of discussing one type or another. We will unify and have algorithms for all of this at the same time. Okay. The nodes in the graph will represent the random variables, and this is very important. The lack of edges in the graph will imply conditional independence assumptions. In other ways, if I have nodes representing random variables, and I have, let's say, 10 variables, and I connect each variable with every other variable, then there's no point of doing graphs, because that problem complexity will never allow you to go anywhere. But if somehow some edges are missing, that implies immediately some variables don't depend on other variables, and that's what we need to take advantage. So the idea is we are interested in graphs that they are not fully connected, right? If they are fully connected, we're not gaining anything by learning this course. Right? The idea is not everything depends on everything, and we need to learn, and that's part of the structure problem that we discussed at the second part of the course. But again, the lack of edges is what represents conditional independence assumptions, and we will spend 2 or 3 lectures to discuss that, and I will give you a number of homework problems to work on. All right, so some pictures. Let's go from right to left. This is a directed graph. I'm going to give you the terminology in follow-up slides, but just to get things going, basically here you can use common sense interpretation for now. So all of these are random variables. So you have A, B, C, D, E are random variables, can be continuous or discrete, it doesn't really matter. And the idea here of these arrows means that C depends on A and B, E depends on C and D, all right? And so this implies this direction of the arrow, a causal relation, all right? So D doesn't depend on E, it depends on D. That's what I know from here, okay? The rest you would need to derive from the factorization applied by this directed model. Now, on this undirected graph, there is no arrows, okay? So obviously, if there is no arrows, and you see these connections, obviously C is related to A and B, obviously C is related to E and D and to B and D, so you see these cliques here, that's this interconnected sets of nodes. So those imply really correlations, but there is no directional component. So in essence, the effect of C on D and D on C has no direction, okay? So this is very different from what you see in this graph, okay? Now, I'm not going to discuss what this is in detail, right? But this is sort of another type of graph that will allow us to sort of unify those two graphs, okay? And somehow, to do that, you need to introduce these extra squared nodes that effectively explicitly spell out these local functions, these local potentials that you have either in these undirected graphs or in the directed graphs. So these are function nodes, and that's why this is called a factor graph, okay? So these are the random variables, and these are functions, okay? So we would be able somehow to eventually do inference in factor graphs, and that way accounting for inference in both directed and undirected models. Again, you don't need to know any of this, because we will spend many lectures discussing each of this, but I thought you should see this on lecture 1. So nodes represent random variables, edges, dependencies, and really what we're interested is in the lack of edges. So the fact that there's no edge between A and B, that's very important. If you try to connect A to B to D to E, then don't expect to gain anything by doing graph theoretic approaches. Okay, so if you have many nodes, so this is, let's say, high dimensional, this V, let's say it's 100, the first objective when you work with graphs is to come up with the joint probability distribution, and in particularly with a factorized form of the joint probability distribution, okay? A factorized form that somehow can easily be visualized in a graph accounting for whatever independence relations exist between these variables. Now, you can appreciate that if the variables depend, there's no independence relations, right? And each of these variables can take k values. And let's say each of these variables is also discrete and can take k values. How many values, how much information do you need to describe this probability distribution? So you need k values for each of them, and you have v of those. How many variables do you need to describe this joint distribution with no independence relations at all? K to what power? The power of v, right? So if v is 10, forget about it. You won't be able to do anything, okay? So we will see on what we can benefit taking advantage of these conditional independence relations and graphs. Now, once somehow you can come up with the proper factorization of this, then you can start talking about inference. So, for example, if you, let's say, measure the value of variable x1, you know what the value is, then you can say, what's the value of x2 given x1? where the rest of the variables, maybe you marginalize them, okay, if you get rid of them. So obviously, you appreciate that the sum and product rule will come handy to actually manipulate this, but also Bayes' rule will be essential when you have evidence to be able to do inference. Applications really, you know, and there, you just mentioned anything, all right? So in bioinformatics, these are standard methods. In medical diagnosis, actually, almost every, you know, diagnosis now, actually every time I'm reading articles that these automated systems for diagnosing diseases, let's say from images, etc., they operate with much less chances for false alarm than the best doctor in the world, right? They're extremely accurate. So now it's not like this is for mathematicians or computer scientists. People in practice are actually using probabilistic graphical models for prognosis or diagnosis of diseases. Computer vision, speech recognition, Google Translate. I mean, I use it, you know, when I go to China, I always say something and it translates, and I always see what it translates to be sure it translates correctly, because sometimes I say something and I read it, it's like, wow, I'm going to get in trouble, all right? And so, but it really works very well, okay? I mean, I have seen it even working when there are several people speaking simultaneously with accent, and it does miracles. So it's really a direct application of probabilistic graphical models. Practically every topic, every algorithm in machine learning can be posed on a probabilistic graphical model form, okay? So we may, I don't know if we're going to have time, I cover a little bit ideas of latent variables and model reduction in the fall. So we may spend a lecture or two to go back and address those and generalize them using graphical models. So if you don't know anything about those algorithms, it's fine, because when we post them in graphs, we will post them as new problems, and so you will see sort of a modern aspect of these algorithms, and I think, you know, you will like that more than equations that without the means to visualize them. The, you know, error control codes and the way, you know, your computer you know, restarts and figures out what goes wrong, right, and behaves properly, it's really based in probabilistic graphical models. If you take, for those in engineering, if you take sort of, you know, we talk about few random variables here and there, but actually this concept of probabilistic graphical models can be extremely effective, where these nodes, they're not simply random variables, but they're interconnected, complicated systems of different origin, a mechanical model, a thermal model, etc. And each of them has its own random variables in within, right? But you have interconnected systems that speak to each other. And this is really sort of an important area for development, because it poses a lot of challenges, because a lot of these systems are governed by models that are very computational, very expensive. So lots of the methodologies for doing inference would not be able to sort of work directly. You would have to do something there to simplify the representation of the systems. Okay, so let's you know, go fast through notations. Nodes, random variables, edges, we already said probabilistic relations. The lack of edges basically will provide information on independence relations. So a graph has a number of nodes, has a number of edges, the number of nodes from 1 to v, the number of edges. If we have a directed graph, basically it will be this pair S comma T, where the edge goes from the arrow goes from S to T. Okay. Now, to really extend this to both undirected and directed graphs, you have to use what's called an adjacency matrix. So you define the adjacency matrix G of S and T. These are nodes equal to 1 if the edge S comma T is in this set, all right? And this allows you to extend this to undirected graphs, because if you have G of S comma T equal to 1 and simultaneously G of T comma S equal to 1, right? Then this is an undirected graph. There is no going from S to T and T to S is the same, okay? So 2 examples. And I threw lots of terminology here that's going to come in the following slides, but it helps to see them several times. So you have nodes 1, 2, 3, 4, 5. I am going to call node 1 the root, all right? Can you give me, without actually even reading the follow-up slides, just look on the graph, what do you think the root will be? I mean, what would be a good definition? I mean, you notice, okay, there are arrows from, so in other ways, why, the root is not 5 and it's 1? What will be a good definition? Right. So I am repeating the answer here. In this case, 1 has no arrows coming to it. Okay, and as we will see, this implies, following a definition that's going to come up, that 1 has no parents. Okay, and with that definition, 5 then, that is the leaves of the graph, 5 has no children. Okay. So 5 has no children. So in that sense, 1 is the parent of 2, all right, and 3. Here, 4 has 2 parents, 2 and 3, okay, etc. And let's see what else comes here that's important. And it says, again, this is coming up later, but I want you to see it hundreds of times so we can communicate. It says this directed A means has no cycles, acyclic graph, all right? You notice has no cycles. Someone will say this is a cycle, but actually, because this is a directed graph, you notice when I go the direction of the arrows, here I cannot go from 4 to 3, so there are no cycles there. Okay? All right, so we discussed this. And then it says the nodes are numbered in topological order. So what does that mean? That's very essential for directed graphs. What do we mean topological order? Just looking at this graph, basically, what will be sort of your imagination here? What does, so the numbering, it says in topological order. So, I mean, could I have called this 1, 2, 3, 4, 5? All right, so that's a good definition here indeed, right? Since we define the root to be the node that has no parents, all right? So basically, we have to start numbering from the root to the leaves, basically, okay? And that's a topological order. Now, if it's a more complicated graph, this may not be a unique topological order, all right? But for now, you start, basically, you're not going to assign to the children nodes that they are earlier in the order of numbering than the parents. All right, so you number the parents and the children. That's the idea here. Okay, so 2 and 3 are the children, so 1 will be there, 2 and 3 will be there. Similarly, these are the parents of 4, so the numbering of topological order makes sense. Okay, the same graph now if it was an undirected graph. Okay, I'm throwing in lots of things because I want you to see those things hundreds of times, and there are details that are going to be discussed with lots of simple examples in follow-up lectures, right? But I want you to see these things now. So in some sense, I'm claiming that the graph that you see here, it is very much the same as that graph, but I see there is something going on that's a little bit different. What's the difference between the two graphs when you look at them? Okay, there are no arrows, but there is something else that is different. So what is different immediately when you visually look at this? 2 and 3 are connected. And that's an essential step when you go from directed graphs to undirected. So what are the 2 and 3 nodes? What is common between 2 and 3? They are parents of? No. They are parents of what? Of 4. So when you go from a directed graph to undirected, what you need to do is you need to be sure the parents are married, because this is Notre Dame. We don't allow unmarried parents, okay? So we marry them, all right? And this process, mathematically, is called a moralization process, okay? People will think that I'm, my lecture has religious connotations, but that's the terminology, moralization process, okay? So you basically have to marry the parents, okay? And actually, immediately you can see when you marry the parents, you get loops in this graph, okay? So suddenly you went from no loops to 2 loops, right? And that has implications in the way we're going to treat this process. Now, in the graphs, once you moralize, you marry the parents 2 and 3, you define what is called cliques. And in particular, of interest here is what is called maximal cliques. Okay? So, cliques is a set of interconnected nodes. Okay? So, for example, if this is 1, 2, and 3 is a clique, right? Because 1 is connected to 1 is connected to 3, and 2 is connected to 3. All the nodes are interconnected. Now you say, is 1, 2, 3, and 5 a clique? Why not? 1 and 5 are not connected, right? 2 and 5, 3 and 5 are not connected, okay? So 1, 2, and 3, 2, 3, and 4, and 3 and 5 are what we call maximal cliques. And I can tell you, and this will come in 4 or 5 lectures, I don't know, the idea of identifying these maximal cliques will be that when we take a joint probability distribution of these 5 random variables, we're going to be able to write the joint distribution as the product of potentials with each potential defined on maximal cliques. So there will be local potentials, but each potential will be on a maximal clique. And that will be actually an amazing theorem which we're going to prove, right? That somehow, if you have a graph like that and a probability distribution defined on this graph, then that you can decompose it on potentials defined over these maximal cliques. Okay? Again, treat all of this as sort of on the air ideas, because we will discuss those as we go further in the course. Okay, so let's see. The parents of a node, right, are, you remember how do we define what was the name of G? This is the adjacency matrix. So the parents of a node S are all the nodes T where G of T comma S is equal to R. So for example, the parents of node 6 are 2 and 5, okay? And you can denote this as pi of 6 equal to 2.5 or x pi 6, different notations. I think This is basically both notations are the ones used by the Michael Jordan's book. The children of node S are basically the nodes T such that G of S and T equal to 1. The family of a node, all right, is S and the parents of S. I'm actually, when I was looking, it's like, you know, why they don't like the children, all right, but somehow that's why maybe I never used the terminology family, but until we find that this is not the right definition, this is what it is there. So the family is S and the parents of S. We already discussed root is the node no parents, leaf the node no children. The ancestors of a node T are all the nodes S where there is a path from S to T. And if it's a directed graph, this path has to be a directed path. If it's undirected, basically any path from S to T will do it. And the descendants of a node S are all the nodes, all right, that you can find the trail from S to T. And again, in directed graphs, this trail will have to follow the arrows. So these are the ancestors and those the descendants. The neighbors, and it doesn't matter what type of graph you have, are the immediately connected nodes. So the neighbors of S are all the T's where either G of S and T equal to 1 or G of T of S equal to 1. Okay, so in defining the neighbors, even if it's a directed graph, the orientation it's not important. So the degree of a node is the number of neighbors, and in particular you will see this in lots of machine learning books. The in and out degrees basically count the number of parents and the number of children. So when they say the in degrees, the number of parents, the out degrees, the number of children. And this is sort of an important concept because when we write the joint probability distribution, we will see the factorization will scale basically with this in degrees with the number of parents, okay? And I may actually show you in a slide shortly. We already discussed the concept of a directed cycle, all right? So in this diagram here, there is no directed cycle, but you notice on this there is one, okay? On this, there is no directed cycle, all right? So a directed acyclic graph is a directed graph with no directed cycles, okay? And most of the graphs we're going to use will be directed acyclic graphs, but you know, when we generalize, we will be able to go away without. Okay, this concept of a tree and a directed tree is very essential because algorithms on tree are the easiest to implement. All right, and you know, we wish that every graph was a tree, because if it's a tree, we can do inference in seconds. So this sort of would be an ideal situation. So an undirected tree is an undirected graph with no cycles. All right, and for an undirected tree, there is a single path between any pair of nodes. Okay, and I'm starting with this, right, because I will be able to define this concept of polytree for directed graphs. I'm going to need an undirected tree. So an undirected tree is an undirected graph with no cycles. Okay, so for example, did we have an undirected tree somewhere? There are cycles here, so this is not good. Do we have any picture? Anyways, doesn't matter. I don't see. Maybe we'll want to come. All right, where are we? So an undirected tree has no cycles, and there is a single path from any pair of nodes. Now, a directed tree is a directed acyclic graph in which every node has at most one parent. can you tell me why do we want one parent? And how is that going to be connected with the moralization process that I mentioned before? It says a directed tree is a DAG in which every node has at most one parent. You remember I threw in the air this equivalency of a directed tree with an undirected tree after we did some operation which we call it moralization. So here I say directed tree is a DAG in which every node has at most one parent. So why do I throw this thing has one parent? Because if it has two parents, then what is going to happen? When we transform it to an undirected graph, we will marry those parents, and as a result, we will get a cycle. Right? So a directed tree needs to have, every node has at most one parent. Okay? Now, so this will be ideal situations, right? You have an undirected tree or a directed tree. Now, if we have a directed acyclic graph that has more than one parent, right? And we moralize it, effectively we will get, we will get cycles. But if the undirected graph that we get is a tree, all right, then we can call this, the directed graph is called a polytree. Okay? So let's see some examples here. Can you tell me which of these graphs is a tree and which one is a polytree, or, what is this graph? Is this a tree? According to our definition, right, of a directed tree is every node has at most one parent. Does this look to you like a tree? Right? So if you actually transform this to an undirected graph, right, there will be no moralization step. So you're not going to connect this node and that because, this has this as a parent, that has that as a parent. So you have, every node has one parent. So there will be a single path from every node to any other node. So this is a tree. Now, why is this a polytree? It looks like a simple tree, but actually it's a polytree. The reason is what? This node has how many parents? It's two. So when you merge them, all right, and you make this an undirected graph, yes, there is a single path from every node to any other node, but there is a cycle here. Okay? Now, obviously, the algorithms will get a little bit more complicated when you have a polytree, but actually, when you transform this to that third format of graph that I call it a factor graph, that you will see that you can treat a polytree basically. A polytree will become actually a tree, okay? And then you can apply the standard algorithms that we will see in this course, okay? But you will need to change the way the graph is defined. So for now, think this will be a fantastic if all graphs look like that. This will also be fantastic. It's a little bit more complicated, but somehow we will be able to develop algorithms that have the same complexity as if we were working on a tree. Okay, so this is basically the same thing we just discussed. And the same thing here. So we talked about cliques and maximal cliques. So there is this concept of a clique is only defined for undirected graphs. And again, a maximal clique is the highest number of interconnected nodes. And the highest number means you cannot go and consider adding another node to the clique without violating that property. Okay? So this would be an essential development. So here is a directed graph. When you moralize this to make it an undirected graph, it looks like that. Okay, so what parents have I married here? 2 and 3, right? 5 has 2, and let's see, 7 has how many parents? Has 3 of those, right? How is it possible to have 3 parents? Well, in some religion is allowed, okay? So we marry 4 and 5, 4 and 6, okay? All right. And again, I'm throwing this just to see it for now, but we're going to discuss this in details, right? So, just remember what this process of parallelization means, and somehow we haven't proved that this is equivalent to this, and whatever, I haven't even said what equivalent means, right? So we will see when we discuss about factorization of the joint probability distribution of the two graphs. All right, so I have 5 minutes to go, right? So let me give you, without any proofs or anything like that, okay, because we will come back to this, how a joint probability distribution of these 7 variables is decomposed based on the graph that you see, okay? So the notation x1 to 7 means this is the joint probability of x1, x2, x7. And now if you don't have a graph, right, and somebody gives you the P of x1 to x7, the product rule from probability theory tells you what is going to be the right-hand side. I mean, without looking at this, right? So you don't look at this. What is, from probability theory, what's the joint of variables of the P of x1 to x7? How are you going to write this? Would be P of x1 times what? P of x2 given what? x1, then P of x3 given x1 and x2, etc. Now, if you notice here, I'm claiming, well, it's actually much simpler than that. I say it's P of x1 times P of x2 given x1, P of x3 given x1. You notice there are, in the worst case, there are like 3 arguments in the condition. Can you look at the graph and look at this equation and tell me, again, I'm proving nothing, right? I'm throwing it there. And can you look at this and somehow imagine what the graph tells you that somehow extracts us this equation without any derivation? Right, so basically each of these factors is, so every node has a factor, right? And in this case, this factor is a probability, it's a conditional probability distribution of the variable in that node condition on its parent. So here I have the probability of x1 condition on the parents of x1. What parents x1 has? None. x2 condition on the parents, which is 1. x3 condition on the parents, which is 1. x4 condition on the parents, which is 2. x5 on 2 and 3. x6 on 5 and 3. And x7 on 4, 5, and 6. Now, the reason that this looks way simpler than what the product rule would tell you, right? The product rule, for example, we have x of 7, condition of x1, x2, x3, x4, x5, x6. The fact that you don't have x1, x2, x3, x2, x3 means that x7 is independent of the variables x1, x2, x3, given the variables x4, x5, and 6. Now, I have not proved anything. I'm just telling you what the answers will be when we do the proofs. Okay? So somehow, look at that graph, you should be able to immediately, just from the graph, write a decomposition that you know is the correct decomposition. So you don't have to do calculations by hand and try for 10 hours and this and that. Immediately you can transform this and you can get that. Now, this, it's, if we had 7 variables and each variable takes k values, with non-independence relations, right? I'm going to need k to the 7th to describe the joint probability distribution on the left-hand side. But you notice these are requiring sort of probability tables that are of smaller size. So let's say P of x1, you need k values. P of x2 given x1, k squared. I'm not accounting here for the normalization of these probabilities to make life easy. This is k3 and this is k4. So basically, if you have the independence relations that you see in the graph, we haven't really proved anything again, I emphasize. This is lecture 1 to just scare you, so you can not come on Thursday. But this, it's k to the 4th versus if you had no independence at all, which would be k to the 7th. Okay? So independence relations. And independence relations in the graph, imply from the fact that, let's say, node 2 and 3 are not linked, right? 2 and 7 are not linked, 4 and 6 are not linked, 1 and 7 is not linked. So this lack of edges between nodes is what leads to this factorization, and that's very nice because you can read it on the graph, because each of these distributions is a factor of the probability of its node condition in its parts. All right, 1:45, that's when we're supposed to finish? All right, so I'm going to continue on this lecture with a few more examples, and then we will take things slowly and discuss all the details on directed graphs, and we will move from there. So the website, I will try to put the lecture up at the latest by tomorrow. Okay, at the latest by tomorrow. Okay, and actually I'm going to send to those registered. I'm going to send a copy of at least the introductory chapter from Jordan's book, so you can start reading them. All right, so I'll see you on Thursday.